The universe is missing something, not a small amount, not a rounding error in the calculations or a marginal discrepancy that better instruments might resolve. The universe is missing approximately 85% of the mass it should contain. 85% of everything. When astronomers calculate how much mass the universe needs based on how galaxies rotate, how clusters of galaxies hold together, how the large scale structure of the cosmic web formed from the nearly uniform matter of the early universe, the number they arrive at is vastly larger than the number they get when they add up everything they can see. Every star, every planet, every gas cloud, every dust grain, every black hole, every neutron star, everything that emits light, absorbs light, reflects light, or interacts with light in any way that makes it detectable by any instrument human beings have ever built. All of it together accounts for approximately 5% of what should be there. 5%. The universe we can see, the universe of stars and galaxies and nebulae and planets that has occupied human attention since the first person looked up at the night sky and wondered, is a thin, visible film on the surface of something vastly larger and entirely invisible. We call it dark matter, not because we know what it is, because we do not know what it is. And the word dark is the most honest description available for something that does not emit light, does not absorb light, does not reflect light, and interacts with ordinary matter in no way that any detector we have built has ever been able to confirm. It is dark in the way that absence is dark, in the way that the space between galaxies is dark. Not because it is color dark or made of dark substance, but because it produces no signal of any kind that our instruments can detect directly. And yet it is there. We know it is there with the same confidence that astronomers knew Neptune was there before anyone had seen it, not from direct observation, but from the gravitational influence it exerts on everything around it. The galaxy you live in would not exist without it. The large-scale structure of the universe, the cosmic web of filaments and clusters and voids that defines the architecture of everything on the largest scales, would not have formed without it. The galaxies we observe would spin themselves apart without it. The evidence for dark matter is not the evidence of a single anomalous measurement or a puzzling result from one experiment. It is the convergence of four completely independent lines of evidence, each one discovered separately, each one studied by different scientists using different instruments and different methods, all pointing to the same conclusion. Something invisible is out there, and it outweighs everything we can see by a factor of 5 to 1. If this is the kind of content you want more of, subscribing to The Cosmic Depth takes 2 seconds, and we post new documentaries every few days, because the story of dark matter is one of the strangest stories in modern science. Not because the evidence for it is weak. The evidence is overwhelming. But because 40 years of increasingly sophisticated experiments specifically designed to detect it directly have found nothing, not a whisper, not a candidate event that survived scrutiny, not a single confirmed particle of dark matter in any detector anywhere in the world. We know it is there. We cannot find it. We do not know what it is. And those three facts together constitute one of the deepest unsolved problems in all of physics. To understand why this is so disturbing, you need to understand where the missing mass problem came from. because it did not arrive as a theoretical prediction or a mathematical curiosity. It arrived as an observation, a real measurement of real galaxies producing a real result that refused to make sense. The year was 1970. The astronomer was Vera Rubin. Rubin was studying the rotation of the Andromeda Galaxy, our nearest large galactic neighbor, the most distant object visible to the naked eye, a spiral galaxy containing hundreds of billions of stars spread across a disk roughly 200,000 light years across. She was measuring how fast different parts of the galaxy were rotating around its center. The physics of this seemed straightforward. A galaxy is a gravitational system. Its stars orbit the galactic center, under the influence of the combined gravity of all the mass in the system. The further a star is from the center, the further out in the disk it sits, the weaker the gravitational pull it experiences from the mass inside its orbit, and therefore the slower it should travel. This is exactly how the solar system works. Mercury, the innermost planet, orbits the Sun at 47 kilometers per second. Neptune, the outermost planet, orbits at only 5.4 kilometers per second. The further from the mass concentration at the center, the slower the orbital speed. This relationship, called Keplerian rotation after Johannes Kepler, who described it for the planets 3 centuries ago, was expected to hold for galaxies just as it held for planetary systems. Rubin measured it and found that it did not hold. The stars in the outer regions of Andromeda were not orbiting more slowly than those near the center. They were orbiting at approximately the same speed. The rotation curve, the graph of orbital velocity plotted against distance from the galactic center, was flat, not falling off as Kepler's laws predicted. Flat. This was not a marginal discrepancy. It was a fundamental violation of what the known mass distribution of the galaxy should produce. If the only mass in Andromeda were the visible mass, the stars and gas clouds whose light Rubin could observe, the outer stars would be orbiting far too fast. They should fly off into intergalactic space. The galaxy should tear itself apart. It was not tearing itself apart, which meant there was mass that Rubin could not see. A vast halo of invisible mass extending far beyond the visible disk of the galaxy. Far larger than the visible galaxy, far more massive, providing the gravitational pull that kept the outer stars in their orbits at the speeds she was measuring. Rubin checked her measurements. She checked her analysis. She studied other galaxies. She found the same thing in every one she looked at. The rotation curves were flat. The visible mass was insufficient. The missing mass was enormous. She published. The results were contested. The measurements were repeated by other astronomers using different instruments and different methods. The flat rotation curves held up. Every galaxy studied showed the same pattern. The invisible mass was not a measurement error. It was a feature of every galaxy in the observable universe. The missing mass problem was real, and it has been real ever since. In the decades following Rubin's work, the question shifted from whether dark matter existed to what it was. The evidence accumulated from multiple directions. The case became not just compelling, but overwhelming. The kind of overwhelming where the question is no longer whether to believe it, but whether any alternative explanation can possibly account for all of it simultaneously. The answer to that question is the heart of one of the most fascinating and unresolved debates in modern physics, And it starts with four pieces of evidence that each, on their own, would be sufficient to take dark matter seriously, and together constitute one of the strongest empirical cases for any unseen entity in the history of science. Four independent lines of evidence. This is the phrase that matters most when evaluating the case for dark matter. Not one anomalous measurement that might be explained away. Not a single puzzling result from one instrument that might be a systematic error. Four completely separate observations discovered by different scientists at different times using different methods, each one pointing independently to the same conclusion. When four independent roads lead to the same destination, you begin to trust that the destination is real. The first road is the one Vera Rubin walked. Galaxy rotation curves. We covered the essential result in the previous section. The flat rotation curves that every spiral galaxy displays, the orbital velocities that refuse to drop off with distance the way Kepler's laws demand, the invisible mass that must be present to prevent the outer stars from flying apart. But the full weight of this evidence is not captured by the story of one astronomer and one galaxy. Rubin and her colleague Kent Ford spent years measuring the rotation curves of dozens of galaxies. Other astronomers measured dozens more. The pattern was universal. Every spiral galaxy studied, regardless of its size, its luminosity, its distance from us, its position in the universe, showed the same flat rotation curve. The visible mass was always insufficient. The invisible mass was always present. The ratio of dark matter to ordinary matter was roughly the same everywhere. Approximately 5 times as much dark matter as visible matter in every galaxy studied. Not approximately 3 times in some and 10 times in others. Approximately 5 times consistently across systems spanning a vast range of sizes and luminosities and distances. This consistency is important. It is not what you would expect from measurement error or systematic bias. Systematic errors in astronomy tend to be specific to particular instruments or particular methods. They do not produce the same consistent ratio across independent measurements made by different research groups using different telescopes in different decades. The consistency of the 5-to-1 ratio across such a diverse range of galaxies is itself evidence that something real is being detected. The second road is gravitational lensing. Einstein's general relativity predicts that mass curves spacetime and that this curvature bends the path of light. A massive object between us and a more distant light source will deflect the light from that source, acting as a gravitational lens, distorting and magnifying the image of whatever lies behind it. The amount of deflection depends on the mass of the intervening object. Measure the deflection, and you can calculate the mass. When astronomers measure the gravitational lensing produced by galaxy clusters, the most massive bound structures in the observable universe, containing hundreds or thousands of galaxies, along with hot gas visible in X-rays, they consistently find that the deflection is far larger than the visible mass of the cluster can explain. The visible matter in a galaxy cluster, the individual galaxies and the hot intergalactic gas, accounts for perhaps 15 to 20% of the mass required to produce the observed lensing. The rest, the 80 to 85% that must be present to explain the bending of light, is invisible. This is a completely different measurement from the rotation curve method. It doesn't depend on the orbital velocities of stars. It depends on the bending of light by gravity, a phenomenon described by general relativity that has been tested and confirmed in dozens of independent contexts. The calculation is straightforward. The result is clear. There is far more mass in galaxy clusters than the visible matter can account for. And it is the same invisible mass, the same 5-to-1 ratio, the same dark matter. The third road comes from the cosmic microwave background. The CMB is the oldest light in the universe. The afterglow of the Big Bang, emitted when the universe was approximately 380,000 years old and cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was opaque, a hot, dense plasma through which light could not travel freely. After that moment, the moment of recombination, light streamed freely through space and has been traveling ever since. We detect this light today as a faint glow of microwave radiation arriving uniformly from every direction in the sky. Its temperature is approximately 2.725 Kelvin, just a few degrees above absolute zero, and it is extraordinarily uniform, but not perfectly uniform. There are tiny variations in temperature across the sky, fluctuations of approximately 1 part in 100,000, that encode the structure of the early universe at the moment of recombination. The pattern of these fluctuations, their size distribution, their statistical properties, the specific angles at which they cluster, is a direct record of the acoustic oscillations that rippled through the early universe before recombination. Waves of compression and rarefaction in the primordial plasma, driven by the interplay of gravity and radiation pressure, that left their imprint in the temperature map of the CMB. The specific pattern of these oscillations depends on the composition of the universe, on how much ordinary matter was present, on how much dark matter was present, on how much dark energy was present. The oscillations are sensitive to these quantities in ways that cosmologists can calculate precisely. When cosmologists fit the observed CMB temperature fluctuations to theoretical models, they find that the best fit requires approximately 5 times as much dark matter as ordinary matter. Not dark matter as a vague placeholder for missing mass, but dark matter with specific properties. Specifically, that it is cold, meaning it was moving slowly relative to the speed of light in the early universe, and that it does not interact with light, meaning it was not part of the photon-baryon plasma that produced the acoustic oscillations. This tells us something important. The dark matter was not oscillating with the ordinary matter in the early universe. It was not coupled to the radiation. It was already separate, already invisible, already non-interacting before the CMB was emitted. Whatever dark matter is, it was dark from very early in the history of the universe, and the CMB evidence for it is completely independent of the rotation curve evidence and the lensing evidence. It does not depend on measuring orbital velocities or light deflection. It depends on the acoustic physics of the early universe, on the specific pattern of temperature fluctuations that the composition of the cosmos left in the oldest light in existence. 3 independent methods, 3 times the same answer. The fourth road is the large-scale structure of the universe. The cosmic web, the vast network of filaments and clusters and voids that defines the large-scale architecture of matter in the universe, did not arise from nothing. It grew from the tiny density fluctuations in the early universe amplified by gravity over billions of years, as matter fell into slightly denser regions and left slightly emptier regions progressively more empty. The rate at which this structure formed, how quickly the cosmic web developed from the nearly uniform early universe to the highly structured cosmos we observe today, depends critically on how much matter was present and what kind. Ordinary matter, the matter that interacts with light, was prevented from clumping under gravity during the early universe by radiation pressure. The photons in the hot plasma pushed back against any compression, slowing the growth of structure. Dark matter does not interact with radiation. It was free to begin clumping under its own gravity from a much earlier time. It formed the gravitational scaffolding into which ordinary matter later fell, the invisible skeleton around which the visible cosmic web assembled itself. Without dark matter, the cosmic web would look different. It would be less structured. The clusters would be less massive. The filaments would be less defined. The voids would be less empty. The large-scale structure would be smoother, more uniform, less dramatic than what we observe. Cosmological simulations that include dark matter, that model the universe from the initial conditions of the CMB through 14 billion years of gravitational evolution, produce a cosmic web that matches the observed large-scale structure with extraordinary precision. The filaments are in the right places. The clusters have the right masses. The voids have the right sizes. Simulations that remove dark matter and keep only ordinary matter produce a universe that looks nothing like the one we live in. The large-scale structure of the observable universe is a fossil record of 14 billion years of gravitational evolution. And dark matter is written into that record as clearly and as indelibly as the rotation curves and the lensing and the CMB. 4 roads. Galaxy rotation curves showing that every spiral galaxy contains 5 times more invisible mass than visible mass. Gravitational lensing showing that galaxy clusters deflect light far more than their visible contents can explain. The cosmic microwave background showing that the specific pattern of acoustic oscillations in the early universe requires 5 times more dark matter than ordinary matter. The large-scale structure of the cosmic web showing that the universe would look completely different without dark matter's gravitational scaffolding. 4 completely independent measurements. 4 different physical phenomena. 4 different epochs in cosmic history from the early universe to the present day. One answer: something invisible, something that does not emit or absorb or scatter light, that does not interact with electromagnetism in any way we have been able to detect, makes up approximately 85% of the matter in the universe. This convergence of evidence is what makes dark matter so difficult to dismiss. You can question one measurement. You can explain away one anomaly. But when 4 independent physical phenomena all point to the same invisible component of the universe, when removing that component breaks 4 separate lines of observation simultaneously, the case becomes difficult to argue against on purely empirical grounds. The problem is not whether dark matter exists. The problem is finding it. And this is where the story takes a turn that nobody anticipated. Because the same physics that tells us dark matter must be there also suggests how we might detect it. And the experiments built to detect it, increasingly sensitive, increasingly sophisticated, running now for decades in underground laboratories around the world, have found nothing. Not almost nothing. Nothing. The search has been going on for 40 years. Not a casual search. Not a preliminary investigation with limited resources. A dedicated, coordinated, globally distributed scientific effort involving some of the most sophisticated detectors ever built. Instruments designed with extraordinary precision specifically to catch dark matter in the act of doing the one thing it must occasionally do if it exists in the form that theory predicts: interact. The leading theoretical candidate for dark matter. For most of the last 4 decades, the dominant hypothesis, the one that drove the design of most major detection experiments, is a class of particles called WIMPs, weakly interacting massive particles. The name is not a description of their personality, it is a precise statement of their physics. Massive, meaning they have significant mass, roughly in the range of 10 to 1,000 times the mass of a proton. Weakly interacting, meaning they interact with ordinary matter through the weak nuclear force, one of the four fundamental forces of nature, the same force responsible for certain types of radioactive decay. The weak force is called weak not because it is feeble in any absolute sense, but because it operates at extremely short ranges, inside atomic nuclei, and produces interaction rates far lower than those of electromagnetism. Particles that interact only through the weak force and gravity are extraordinarily difficult to detect. Neutrinos interact through the weak force, and they pass through the Earth as though it were not there. Billions of them flowing through your body every second without leaving any trace. But not quite zero trace. Occasionally, a neutrino interacts. Rarely, but not never. And if dark matter particles are WIMPs interacting through the weak force, they too should occasionally interact with ordinary matter. Not often. The cross-section, the technical measure of how likely an interaction is expected to be tiny. But in a large enough detector, running for long enough, with background noise reduced to sufficiently low levels, a WIMP should eventually announce its presence. It should occasionally scatter off an atomic nucleus in the detector material, depositing a small amount of energy that the detector can measure. This was the prediction. The experiments were built. The most sensitive is currently Lux Zeppelin, a detector containing 10 tons of liquid xenon buried 1.5 kilometers underground in the Black Hills of South Dakota, in a mine that was once the deepest gold mine in North America. The depth is not incidental. The rock overhead acts as a shield, absorbing the cosmic rays that constantly rain down on the Earth's surface, and that would otherwise flood the detector with background signals. At one point, 5 kilometers underground, the cosmic ray background is reduced by a factor of millions. The liquid xenon is ultra-pure, stripped of radioactive contaminants to a degree that makes it one of the cleanest large volumes of any substance on Earth. Any particle that passes through the xenon and causes an interaction produces a flash of light and a burst of free electrons. A double signal that allows the detector to distinguish between different types of interactions and to localize where in the detector the interaction occurred. Lux Zeppelin is so sensitive that it can detect energy depositions of a few kiloelectron volts, a few thousand electron volts, from a single nuclear recoil. It can detect individual photons. It can identify the origin of a signal to within centimeters inside 10 tons of xenon. It has been running. It has been analyzing its data with extraordinary care. The results have been published. No WIMPs. Not a single confirmed WIMP interaction in any of the data collected. Luck Zeppelin is not alone in this. The Zenon experiment at the Gran Sasso Laboratory under the Apennine Mountains in Italy, running in various forms since 2006 and currently operating as Xenon T with 5.9 tons of liquid xenon, has also found nothing. Panda X in China, Deep in Canada, Dark Side in Italy, experiment after experiment, ton after ton of detector material, year after year of running. And the result is always the same. Nothing. The significance of this silence is not merely that dark matter has not been found. It is that the experiments have become so sensitive that they have ruled out large regions of the parameter space where WIMPs were expected to live. The interaction cross-section, the probability of a WIMP interacting with an atomic nucleus, has been pushed lower and lower by each null result. WIMPs interacting at rates that theoretical models once considered natural have been ruled out. WIMPs at higher masses than expected have been ruled out. WIMPs at lower masses have been ruled out. The region of parameter space where a WIMP could still hide is shrinking, and it is shrinking in the direction of a boundary below which WIMP detectors cannot go. Because below a certain interaction cross-section, the background noise from neutrinos themselves, the neutrino floor, becomes indistinguishable from a WIMP signal. At that level, even a perfect detector with zero background would be confused by the irreducible flux of neutrinos from the sun and the atmosphere and supernovae. The WIMPs are either below the neutrino floor, interacting so rarely that they have effectively not interacted with any of the billions of tons of detector material that has been looking for them, or they do not exist in the form that the leading theories predicted. Neither possibility is comfortable. The search has not been limited to underground detectors. The Large Hadron Collider at CERN, the machine that discovered the Higgs boson in 2012, has been searching for WIMPs produced in high-energy particle collisions. When protons collide at the LHC, the debris produced includes every particle that can be created from that amount of energy. If WIMPs exist at masses accessible to the LHC, they should occasionally be produced, and their production should be visible as missing energy. Momentum that goes undetected because the WIMPs produced do not interact with the detector material and simply pass straight through. The LHC has been looking for this missing energy signature for more than a decade. It has found nothing that cannot be explained by known physics. There is also an indirect detection strategy. If dark matter particles are their own antiparticles, as many WIMP models predict, then when two dark matter particles collide, they should annihilate each other, producing standard model particles in the debris. Gamma rays, positrons, antiprotons. These should be detectable by space-based instruments pointed at regions of high dark matter density. The centers of galaxies, the cores of galaxy clusters, dwarf satellite galaxies where dark matter is thought to be particularly concentrated. The Fermi Gamma Ray Space Telescope has been searching for this annihilation signal for 15 years. Other instruments have looked in the same regions at other wavelengths. No confirmed dark matter annihilation signal has been found. 3 independent approaches: direct detection underground, production at particle colliders, indirect detection of annihilation products, all searching for the same particle, all finding nothing. This accumulating silence has had an effect on the theoretical physics community that might be compared to the slow dawning of an uncomfortable realization. In the 1980s and 1990s, WIMPs were not just the leading candidate for dark matter. They were widely considered the most natural candidate. The WIMP miracle, the coincidence that a particle with mass and interaction strength in the weak force range would naturally produce the right abundance of dark matter in the early universe, seemed almost too convenient to be accidental. Many physicists expected the LHC to produce WIMPs almost as a matter of course. The LHC did not produce WIMPs. The underground detectors did not find WIMPs. The indirect detection experiments did not see WIMPs. This does not mean WIMPs do not exist. They could be hiding below the neutrino floor. They could have masses outside the range currently accessible to the LHC. They could have interaction properties that make them more difficult to detect than the simplest models predicted. The search continues. LEX Zeppelin will continue running. The LHC will continue collecting data. New experiments are being designed and built. But the era of easy WIMP discovery, the period when theorists expected detection to be imminent and experimentalists designed their detectors confident that discovery was a matter of time, is over. And in the space opened up by the WIMP's persistent absence, other candidates have moved forward. Axions were originally proposed not to explain dark matter, but to solve a different problem in particle physics, a puzzling asymmetry in the behavior of the strong nuclear force called the strong CP problem. But axions have the right properties to be dark matter. They would be produced in the right quantities in the early universe. They would be cold. They would not interact with light. And their existence would solve two problems simultaneously. The difficulty with axions is that they are extraordinarily light, far lighter than WIMPs, and they interact even more weakly with ordinary matter. Detecting them requires a different approach. The ADMX experiment uses a microwave cavity inside a powerful magnetic field to convert axions into detectable photons, a process predicted by quantum electrodynamics, but requiring the axion mass to fall within a specific narrow range for the conversion to be efficient. A DMX has been running and has ruled out axions in some of the predicted mass ranges, but the full parameter space of axion dark matter is vast and most of it remains unexplored. Sterile neutrinos are another candidate. Hypothetical heavier cousins of the neutrinos we know exist, which would interact only through gravity and have no weak force interactions at all. They could explain anomalies in X-ray observations of galaxy clusters. A line at 3.5 kiloelectron volts seen in multiple cluster observations that has no obvious explanation from known atomic physics. But the 3.5 kiloelectron volt line has also not appeared in some observations where it should be visible if the sterile neutrino interpretation is correct, and the evidence remains disputed. Primordial black holes formed in the very early universe before any stars existed, have seen renewed interest as a dark matter candidate, particularly after the LIGO gravitational wave detections revealed a population of black holes with masses in a range that was not well predicted by stellar evolution models. If primordial black holes exist in large numbers, they could account for some or all of the dark matter. Constraints from various observations limit the range of masses where primordial black holes could make up all of the dark matter, but they have not been fully ruled out. The landscape of dark matter candidates is broader and stranger than it was 20 years ago, and the persistent failure to detect anything has pushed some physicists to ask a more radical question. What if there is no dark matter at all? What if gravity does not work the way we think it works on galactic scales? What if the observations that point to dark matter are pointing not to a missing particle, but to a flaw in our theory of gravity? That question, and the answer to it, is one of the most contentious and revealing debates in modern physics. In 1983, an Israeli physicist named Mordechai Milgram proposed something that the physics community received with a mixture of curiosity and skepticism. What if dark matter did not exist? What if the anomalous galaxy rotation curves, the flat profiles that Vera Rubin had measured and that had been confirmed in galaxy after galaxy, were not evidence of invisible mass, but evidence that our theory of gravity was wrong? That Newton's law of gravity, which had been so extraordinarily successful at describing everything from falling apples to planetary orbits, was not the complete story? Milgram's proposal was called MOND, Modified Newtonian Dynamics. The idea was simple in its form and radical in its implication. Newton's law of gravity states that the gravitational force on an object is proportional to its acceleration. Double the force, and you double the acceleration. Milgram proposed that this relationship holds at the accelerations we normally experience in everyday life and in the inner regions of galaxies, but breaks down at extremely low accelerations, below a specific threshold that he called a zero, approximately 100 billionth of a meter per second squared. Below this threshold, at the very low accelerations experienced by stars in the outer regions of galaxies, gravity behaves differently. Instead of the familiar Newtonian relationship between force and acceleration, Mond proposes a modified relationship that produces higher accelerations for the same force, more acceleration from less apparent mass. Stars in the outer galaxy orbit faster than Newtonian gravity predicts, not because there is extra invisible mass, but because gravity itself produces a stronger effect at these low accelerations. This is not an ad hoc adjustment. Milgram derived his modification from a specific mathematical form and showed that it predicted the flat rotation curves naturally, not by fitting to the data, but from the modification itself. And it worked remarkably well. The flat rotation curves that stumped Newtonian gravity and required enormous halos of dark matter fell directly out of Mond's equations, not approximately, not as a rough match, as a precise quantitative prediction. Given the distribution of visible mass in a galaxy, the stars and gas, Mond could predict the rotation curve with a precision that rivaled and in some cases exceeded what dark matter models could achieve. Mond also predicted a specific relationship between the total luminosity of a galaxy and the asymptotic velocity of its rotation curve, the Tully-Fisher relation, that was observationally confirmed and that Mond explained naturally, while dark matter models required additional assumptions to reproduce. For galaxies, individual spiral galaxies studied in isolation, Mond worked. It worked so well that it was difficult to dismiss as coincidence. The specific value of Milgram's threshold acceleration, turned out to be related to fundamental cosmological quantities, the Hubble constant, the speed of light, in ways that suggested it might not be an arbitrary parameter, but something connected to the deep structure of the universe. The physics community did not rush to embrace MOND. The resistance was partly sociological. A radical modification of gravity requires overwhelming evidence, and the dark matter hypothesis was already well established by the time MOND appeared. But it was also scientific. MOND had problems, serious ones. The first problem was theoretical. MOND, as originally formulated by Milgram, was not a proper physical theory. It was a modification of Newton's equations without a clear relativistic extension. A complete theory of gravity must reduce to general relativity in appropriate limits. MOND, as stated, did not. This was not a fatal objection. The same could be said of Newtonian gravity before Einstein provided its relativistic extension. But it meant that MOND could not make predictions in regimes where general relativity was important. Gravitational lensing, the CMB, the large-scale structure of the universe. All of these required a relativistic theory that MOND initially could not provide. Various relativistic extensions of MOND have since been proposed. TVES, tensor vector scalar gravity, developed by Jacob Bekenstein in 2004. Rockwell, BIMOND. More recently, the covariant emergent gravity of Eric Verlinde and the relativistic MOND theory of Konstantinos, Skordas, and Tom Zwaschnik. Each of these attempts to place MOND's galactic successes within a proper relativistic framework that can make predictions at all scales. None of them has fully succeeded. And this brings us to the second and more devastating problem for MOND, the bullet cluster. In 2006, a team of astronomers led by Doug Clow published an analysis of a system called 1E0657-558, two galaxy clusters in the process of colliding, caught in the aftermath of their collision and observed at multiple wavelengths simultaneously. The bullet cluster, as it became known from the bullet-shaped shockwave visible in X-ray observations, is a natural experiment that dark matter and MOND handle in completely different ways. When two galaxy clusters collide, several things happen. The individual galaxies, which are mostly empty space containing stars separated by enormous distances, pass through each other like two swarms of bees passing through each other, largely unaffected by the collision. The hot intergalactic gas, which fills the space between galaxies and constitutes the majority of ordinary matter in a cluster, is not so fortunate. The gas clouds interact electromagnetically, slow each other down through ram pressure, and remain concentrated near the point of collision rather than passing through. The result is a spatial separation. The galaxies, moving freely, have traveled ahead of the gas. The hot gas, slowed by the collision, lags behind. Now you need to know where the mass is. In the dark matter picture, the mass is concentrated in the dark matter halos surrounding each cluster. The dark matter interacts only gravitationally. It passes through the collision like the galaxies, unaffected by the electromagnetic interactions that slow the gas. The dark matter should therefore be concentrated around the galaxies, ahead of the gas, in two separated clumps. In the MOND picture, there is no dark matter. All the mass is ordinary matter, galaxies and gas. The gas dominates by mass in the ordinary matter budget of a galaxy cluster. The mass should therefore be concentrated where the gas is, near the center of the collision, behind the galaxies. Gravitational lensing tells you where the mass is. Light bending reveals mass regardless of whether it is visible or invisible. You can map the mass distribution of the bullet cluster by measuring how it distorts the images of background galaxies. The result was unambiguous. The mass, the gravitational lensing signal, was concentrated around the galaxies, ahead of the gas, separated from the gas, exactly where dark matter halos would be if they had passed through the collision unaffected by electromagnetic interactions. The mass was not where the gas was. This was not what Mond predicted. Mond, with no dark matter, placed the mass where the ordinary matter was. The ordinary matter was concentrated near the gas. The lensing signal was concentrated near the galaxies. The discrepancy was not subtle. It was the mass of a galaxy cluster in the wrong location. The bullet cluster became, and remains, the single most cited piece of evidence against Mond and in favor of dark matter as a particle. It demonstrated that mass and ordinary matter could be spatially separated, that mass could be in one place and visible matter in another, in a way that is natural in the dark matter picture and deeply problematic in any theory that replaces dark matter with modified gravity. Mond advocates have not given up. They have argued that the relativistic extensions of Mond can reproduce some features of the bullet cluster if they include additional components, sometimes called dark fields rather than dark matter, which is a distinction that critics find unconvincing. They have pointed to other observations where dark matter models have their own difficulties. Certain configurations of dwarf galaxies, the too big to fail problem, the core cusp problem, where Mond or modified gravity approaches do better than standard dark matter simulations. The debate has not been resolved. It has simply moved to a more sophisticated level. Because Mond's successes at galactic scales are too consistent and too quantitatively precise to be entirely accidental. The relationship between the visible mass distribution and the rotation curve is predicted too well across too many galaxies of too many different types for the agreement to be coincidence. And dark matter's difficulties at small scales, the precise distribution of dark matter within dwarf galaxies, the relationship between dark matter halo structure and the baryonic content of galaxies, certain anomalies in the satellite galaxy population of the Milky Way are real enough that the standard model of cold dark matter is not without its own unresolved tensions. What the Mondi debate reveals, beneath its specific technical arguments and counter-arguments, is something deeper about the current state of physics. We have two problems. Dark matter does not interact with any of our detectors in the way the leading theories predict. The WIMP, the candidate that drove detector design for 4 decades, has not appeared despite experiments of extraordinary sensitivity. This is a problem for the particle physics explanation of dark matter. Modified gravity cannot explain the bullet cluster without invoking additional dark components. It struggles at cosmological scales. It lacks a fully satisfactory relativistic extension. This is a problem for the modified gravity explanation. Both the particle and the modified gravity approaches are in difficulty. Neither has won. And sitting in that space between two struggling explanations is the possibility that something is genuinely missing. not just from our catalog of particles or our equations for gravity, but from our conceptual framework for understanding what matter and gravity and the universe are at their most fundamental level. The answer to the dark matter problem may not be a new particle found in a detector. It may not be a modification of Newton's law found in the rotation curves of dwarf galaxies. It may be something that requires a change in how we think about the relationship between matter and gravity at a level deeper than either WIMP's or MOND currently reaches. What that something is nobody yet knows, but the searching continues, and the universe, patient as always, holds its secret. 40 years. That is how long the serious systematic search for dark matter has been running. 40 years of increasingly sensitive detectors. 40 years of more powerful particle colliders. 40 years of space telescopes scanning the sky for annihilation signals. 40 years of theoretical development producing candidate after candidate, WIMPs, axions, sterile neutrinos, primordial black holes, each one motivated by genuine physics, each one designed with specific detection strategies, each one failing to appear in any experiment designed to find it. In those 40 years, the universe has not been uncooperative. It has given us the cosmic microwave background mapped with extraordinary precision. It has given us the large-scale structure of the cosmic web mapped across billions of light years. It has given us gravitational waves from merging black holes and neutron stars. It has given us the first images of black hole shadows. It has given us exoplanets by the thousands and the chemical signatures of their atmospheres. It has given us the accelerating expansion of the universe and the confirmation that dark energy, an equally mysterious, invisible component, dominates the energy budget of the cosmos. It has not given us dark matter, not directly, not in any detector, not in any collider, not in any observation that conclusively identifies a dark matter particle and measures its properties. And this persistent absence, this 40-year silence from the dark sector, is beginning to feel less like a temporary gap in our experimental reach and more like a signal in itself. A signal that we may be looking for the wrong thing, or looking in the wrong way, or missing something so fundamental about the nature of dark matter that all of our detectors and all of our theoretical frameworks have been aimed at a shadow of the real answer rather than the answer itself. The next generation of experiments will push the search further. The L-Lux Zeppelin detector will continue running and accumulating data. Its successor, a proposed detector called XLZD, combining the resources of the L-Lux Zeppelin, Xenon, and Pandex collaborations into a single instrument containing 40 to 60 tons of liquid xenon, will push sensitivity to the neutrino floor and beyond, using the neutrinos themselves as a calibration signal to extract dark matter interactions that would otherwise be buried in the background. The ADMX experiment and its international counterparts will continue scanning the axion parameter space, moving to higher frequencies and higher sensitivity, potentially covering the mass ranges where axion dark matter is most theoretically motivated within the next decade. The Vera Rubin Observatory, named for the astronomer whose rotation curve measurements launched the modern era of dark matter research, will map the distribution of galaxies and dark matter across the observable universe with a precision that will test dark matter models at every scale from dwarf galaxies to the largest structures in the cosmos. These instruments will either find dark matter or push the constraints so tight that most surviving theoretical models will be ruled out. Either outcome is scientifically valuable. Finding dark matter would be one of the greatest discoveries in the history of physics. Ruling out the remaining parameter space with sufficient completeness would force a genuine confrontation with the alternative that dark matter as a particle does not exist, and that something more radical is required. But there is something worth sitting with before we arrive at the experimental future. Something about what the dark matter problem is actually telling us right now. Not about what it will tell us when it is solved. About what it is telling us in its current unresolved state. In the 40 years of null results and unexplained rotation curves and gravitational lensing signals that point to something that cannot be found. The visible universe, everything we have ever seen, everything every human civilization has ever looked at and named and studied and wondered about, is 5% of what exists. 5%. The stars that have defined our understanding of the cosmos from the moment the first human looked up at the night sky. The planets and moons and asteroids that constitute our solar neighborhood. The nebulae and star clusters and galaxies that fill the deep field images of our most powerful telescopes, all of it, the entire visible universe, is a thin, luminous film on the surface of something vastly larger that we cannot see and do not understand. This is not a comfortable fact. It is not the kind of fact that allows you to feel that science has mapped the territory and identified the contents. It is the kind of fact that reminds you how early we are, how incomplete the picture is. How much of what exists remains entirely opaque to every instrument we have built and every theory we have developed. We live in a universe where the dominant form of matter is invisible to us, where the scaffolding that holds galaxies together, that shaped the cosmic web, that determined the large-scale structure of everything we can observe, is made of something we have never directly detected, whose nature we do not know, whose relationship to the physics we understand remains unclear. This is remarkable, not in the sense that makes you feel small and insignificant, though that feeling is understandable and perhaps appropriate, in the sense that makes you feel the genuine openness of the universe, the genuine incompleteness of our understanding. The genuine possibility that what comes next, the discovery that resolves the dark matter problem, whatever form it takes, will change our picture of reality as profoundly as special relativity changed it in 1905 or quantum mechanics changed it in the 1920s. There are moments in the history of science when a persistent anomaly turns into a revolution, when the thing that would not fit, the thing that every experiment confirmed and no theory could explain, became the clue that pointed toward a deeper and stranger picture of nature than anyone had imagined. The ultraviolet catastrophe, the failure of classical physics to predict the spectrum of black-body radiation, became quantum mechanics. The anomalous precession of Mercury's orbit, the tiny discrepancy between observation and Newtonian prediction, became general relativity. The flat rotation curves of galaxies, the gravitational lensing of galaxy clusters, the acoustic oscillations of the cosmic microwave background, the large-scale structure of the cosmic web, all of them pointing to the same invisible thing, all of them waiting. Dark matter is the ultraviolet catastrophe of 21st century physics. the anomaly that every observation confirms and no theory has fully explained, the thing that is definitely there and cannot be found, the clue that is pointing patiently and persistently towards something about the universe that we have not yet understood. What that something is, whether it is a new particle found in a detector in the next decade, or a modification of gravity, or something stranger than either, we do not yet know. But we are asking the right questions. We are building the right instruments. And the universe that has held this secret for 14 billion years has, for the first time in its history, produced something capable of asking about it seriously. That something is us, and the search continues. If this changed the way you see the darkness between the stars, what fills it, what shapes it, what holds the universe together in ways we cannot yet see, the cosmic depth has more waiting for you. Subscribe, and I will see you in the next one.